Okay guys, so we're going to be moving on to trigonometry for a bit now, and I've written here, there's technically no new content in this chapter since GCSE, but the problems you're going to come across will be more involved than at GCSE level, and some of you may probably not admit this to yourself, but even though you probably looked at these at GCSE, maybe you didn't really understand them properly, or maybe you didn't really get your head around the sine rule and the cosine rule that we've got here. We want to talk in a lot more detail about the sine rule and the cosine rule. We're going to be looking at areas of triangles, so I think you probably know the formula that is for areas of triangles already. And then last of all, we're going to be looking at the graphs of the sine, cosine and tangent functions. And that point 3 that we've got down here then leads us into what we're going to be doing. Actually, I don't think I've even got this microphone on. That will then lead us into what we'll be doing for solving trig equations, okay? So the graphs are going to be incredibly important when we get to that bit there, about helping us to solve trig equations that we've got. So let's just kick off with what we're going to be doing here. Quick recap of right-angled triangles. Right-angled triangles, we've been using these things several times already, okay? So I've said you're probably familiar with the formula, sine theta equals opposite over hypotenuse, but what is the conceptual definition of sine? Well, sine is a function which inputs an angle and it gives the ratio between the opposite and the hypotenuse. And the reason that we're allowed to do that is because for any triangle, for any triangle that has a particular theta, or a particular angle for one of them, and it's right-angled, the opposite divided by the hypotenuse, no matter how large the triangle was, because they're similar triangles, that ratio would always be the same. So here I've said that a ratio just means the relative size between quantities, in this case the lengths. For this reason, sine, cos and tan are known as trigonometric ratios because they talk about the ratios of the sides of different triangles, okay? So we know how to do these kinds of things already. First of all, I've got this triangle here. What out of the three, sine, cos or tan, will I be using to try and find x here? I'm going to use cos because I've clearly got the adjacent and I've got the hypotenuse. So I would start off by writing that cos 20 equals the adjacent over the hypotenuse. Now you've probably spotted this before, but you can actually just swap the thing that you're dividing by and the result just to be able to find them really easily. I don't know if you've ever noticed that pattern before. But in theory, you're multiplying up by x and dividing by cos 20. But you can just imagine that these two things are swapping. So x is 4 divided by cos 20, which is whatever that is. How much? 4.256 or 4.26 centimetres in this case. I'm guessing it's in centimetres. And you know how to do these kinds of things as well. So this one I've already got written in. Clearly we're going to be using tan here. We tend to use tan a lot when we have the two sides that are perpendicular because they refer to this side being the opposite and this side being the adjacent. So tan theta is just the opposite divided by the adjacent. And you know how to do this already from GCSE. To find theta, you do the inverse tan of 5 over 3. Just wanted to add in a quick side note. There is another way that you can write the inverse tan of a particular number. Does anybody know what? Instead of writing tan with a -1, good. An alternative thing is you could write that theta is equal to arc tan 5 over 3. And it's exactly the same thing, it's just we don't use that on our calculators, so we tend to use tan -1. This doesn't mean tan to the -1, it just means it's the inverse of that function. It takes the result and it tells you what was the original input. So there's arc tan, similarly there's also arc sine, and there's also arc cos, which obviously is equivalent to sine inverse and cos inverse. Just in case you ever see that language anywhere, it's perfectly fine for us just to use this already, okay? So next thing I wanted to talk to you about is kind of moving away from right-angled triangles, and we're going to talk a little bit about some other bits with non-right-angled triangles. But before that, I actually thought it would be interesting to talk to you about why it's called sine and why it's called cosine, because it kind of helps us know a few more things. So I've said, have you ever wondered why cosine contains the word sine, why it is actually cosine? So just as a bit of a reminder of some things that come from probably year 7 maths, when you have two angles together that add up to 180, we call them supplementary angles. And if you have two angles which together make up 90, then we call those ones complementary angles. So these two angles that we have here, A and B, in a right angle triangle, we would call them complementary angles because they add up to 90 degrees. So the reason that we call it the cosine is to do with this information that we've got written down here. So if I was going to work out the cosine of 50, looking at this diagram that I've got here, the cosine is the adjacent over the hypotenuse. What is the adjacent over the hypotenuse when you look at 50 for the cosine? It's just x, which is the adjacent, divided by z, which is the hypotenuse. And then when you look at the sine of 40, what is the sine of 40 equal to? Sine of 40 would be the opposite. What's the opposite to the 40? X, and the hypotenuse is z. So actually what we can see here is that cos of 50 is equal to the sine of 40. They must be equal to each other because they're both the same ratio. They're describing the same ratio. So this says here that the cosine of an angle is the sine of the complementary angle. Hence, cosine is actually a short version of saying complementary sine. And you can try that out. You can try thinking to yourself, okay, well, if I'm doing the sine of, I don't know, 32 degrees, that would be the same as the cosine of 90 minus 32, which is 58, okay? So that's actually why we have this language with putting a co in front of something. It's because it's complementary. So I'm just going to write a couple of questions here. If I knew that sine of 30, what is sine of 30 the same as? It's the same as a half, but I want to say, what's it the same as in terms of cosine? It's the same as cosine 60, because we're making those two angles complementary. What about if I said the cos of 10 degrees? What's that the same as? Sine of 90. Since when did 90 and 10 make 90? Sine of 80. And you can also have things that are more like, I don't know, you could have the sine of like 13.2 would be the same as the cosine of 70... 76.8, 80, 90, yeah. So that's why it's called complementary function. And in general, what you might like to think of is that the sine of theta is equal to the cosine of 90 minus theta, and also the cos of theta is equal to the sine of 90 minus theta. And we call this the co-function rule, okay? We're going to learn some other types of ratios in the future. At the moment, we only have sine, cos, and tan. You can also, instead of doing the opposite over the hypotenuse, which is sine, there's another definition, which is the hypotenuse over the opposite. And that one also has a co-version of it, a complementary version of it. So we're going to get to those actually at the end of year 12 when we're in rollover or when we're in year 13. Okay. So it's a little side note, but this probably will pop up throughout our studies. And so I wanted to mention it now so that we've kind of had it on the record. We've looked at this idea of the co-function. Simply by adding a co in front of it, you can just take the complement of the angle and it will still give you the same value. Okay. So we're going to go back to now some non-right angle triangles. We're going to have a look at finding missing sides and angles in any kind of triangle. Now I've got this page for you here, but also if you just go to the very back page of your booklet, you'll find that you've got it there as well. So if you're ever doing any questions and you want to be able to refer to this kind of diagram, then this is quite a useful thing for us to be able to use. So this is the overview. When triangles are not right-angled, we can no longer use simple trigonometric ratios because those trigonometric ratios rely on the fact that it's got a right-angled triangle. And so we must use the cosine and the sine rules. Now, I'm probably not going to go through these in too much detail because we haven't looked at each of... I'm not going to go through them at detail now, but we're going to go through them one by one and remind ourselves of when we use these different kinds of things. But I just want to quickly talk about some of the language. So here, when you have two angle side opposite pairs. So side opposite pairs is where you have an angle and a side and an angle and a side. You've got two pairs that are angle and side opposite. If you have, that's when you would use the sine rule. If you've got two sides that you know and a missing side opposite a known angle, so you've got a side, and a missing side and you know one angle, that's a cosine rule. If you know all three sides and you want to find an angle, you use the cosine rule. And then the last one is a kind of a mixture. If you have two sides that are known and a missing side that is not opposite a known angle, so this one here is not opposite something that we know, you've got an option of what you can do. You can either use the cosine rule or the sine rule twice. I personally prefer using the cosine rule because the thing that the cosine rule has in common, here, here, and here, is each of these triangles for the cosine rule, I'm interested in three sides. I either know two and want to know one, or I know all three of them. The one time that I use the sine rule is where I have only two of the sides, and I couldn't care less about the last one because I'm not being asked to find it. And I find that a little bit easier to help me to decide which of those two that I actually use. So we're going to start off by looking at the cosine rule. Now you do need to know the cosine rule. You needed to know it at GCSE, but you also need to know it at A level as well. It won't be provided in any kind of formula book that we have here. So we use the cosine rule whenever we have three sides and an angle that are involved. Does anybody remember from GCSE this formula for a start? Do you know this formula off by heart? Yeah? And do you know how the sides get labelled? Can you remind me of how the sides get labelled? Yeah, very nice. The length sides are small letters and the angles are capital letters. And what else do we know about the lengths and the sides? The lengths and the angles? Good. Capital A is opposite lowercase a. So when you have a triangle that's like this, if this is lowercase a, this angle is capital A, and then we've got B and C. I'm not bothered about B and C because it doesn't actually really matter. When you look in the formula here, you've got B squared plus C squared. Well, that could have just been C squared plus B squared. And here you've got BC, but actually that could have been CB. So it doesn't matter which way round these things go. So I'm interested in the fact that this is my angle A, and then this is my length of A. The other ones, I don't care which way round it they are. That one's B and that one's C, or the other way round, okay? You'll notice that the cosine rule, it should remind you of something slightly. What does it remind you of? Which other formula that we've used in the past? It's like Pythagoras, okay? It's actually derived, and you can look at this if you want to in your own time. It's actually a variation on Pythagoras' theorem, okay? So you've obviously got A squared, B squared, and C squared, and then there's this kind of extra bit that makes it adjust correctly, okay? So in this case, if we're going to try and find out what A squared is equal to, well, it's not going to be A squared in our case. It is X squared. So our X squared is equal to 12 squared plus 15 squared minus 2 times 12 times 15 times the cosine of 115 degrees, okay? And then I'm just going to put that all into my calculator. You've done it all already? So I've got 12 squared plus 15 squared minus 2 times 12 times 15 times the cos of 115. So x squared is 521 point blah, blah, blah. So x is the square root of that, and we get 22.8. I'm not going to put centimetres because it doesn't even look like I've been told that it's centimetres, but I'll just say it's three significant figures. Okay, no exact value for that, so we'll just leave it in this form. It looks like a sensible answer. If it was 521, you forgot to square root it, you should look at that and just be like, what? How could I possibly have a 15, a 12, and then a 521? So it's always useful to try and think if those kind of things make sense, okay? The next example I've got is how you deal with a missing angle. Now, I don't know if this has happened for you guys, but sometimes people memorize the way that the formula should be with the missing angle as the subject. I personally don't like that, just in case, just for what we're about to come up against where there's more algebra. I personally just like memorizing the cosine rule and then thinking about how things will fit into that. So can I go on to the next bit? So it's looking for this angle over here, which is alpha, bearing in mind that's A, and then this is the side that goes opposite. That's the only thing I'm really interested in when I'm talking about the cosine rule. I would not think about using the rearranged version. I would start off by writing down to myself A squared equals B squared plus C squared minus 2BC cos A, and then I would substitute things in and rearrange from there because it tends to be a little bit easier. So my A squared here is 4 squared, and then you still get your 7 squared plus 9 squared minus 2 times 7 times 9 times cos, and A this time is this Greek letter alpha. So that ends up with 16, and then I've got 7 squared plus 9 squared, which is 130.
Which one did you take as B?
It doesn't matter for B squared and C squared. Either of these ones, they could just be either way round. And the reason why is because you'll either get 9 squared plus 7 squared, or 7 squared plus 9 squared, which is the same. And instead of 2 times 7 times 9, you'd get 2 times 9 times 7, which is the same thing. So the only one that matters is the angle and the side that is opposite it, okay? So you get 130 minus 126 cos alpha. And then the quick way of rearranging these kind of things, where the thing you want has been subtracted, you're adding that to that side and minusing the 16. So I kind of think about these two things sort of swapping places. So you get 126 cos alpha is 130 minus 16. So cos alpha is 130 minus 16, which is 114 over 126. So alpha is the inverse cos of that. Which is 25.2 degrees.
So if you know how to do it, like rearranging the formula stuff, could you just do like that?
You can stick with your rearranged formula if you want to. I don't mind if you want to stick with your rearranged formula. But if you get to a point where you get like tangled up in the algebra, it might be better to go back to the longer version. Okay? So things you should notice here is obviously we're doing the cosine rule, but when you might look at this, you might say to yourself, oh, well, I've got 3 sides. And as soon as you have 3 sides, cosine rule. If you've only got 2 sides and you're not interested in the third side, it's going to be the other rule, which is the sine rule, okay? That's why I've got this little box down here as a bit of a reminder. It's a number 2 here that we're looking at. So I'm going to just do a couple of trickier questions that we have here, and then you're going to try just a few, and then we're going to move on and have a look at the sine rule pretty quickly, okay? So, first of all, how do I identify that this one is a cosine rule question? 3 sides have been labelled, so I'm going to be using all of these, and the 2 that I'm most interested in, the ones that are the distinct ones, is the 60 and the 2x minus 1. This is what my a is, and this is my other bit, which is my lowercase a. So now you can see how this becomes a bit more of a year 12 question, okay? I have a squared, which is 2x minus 1 squared, equals these ones squared and added, which is just going to be x squared plus x plus 8 squared minus 2 times x, which is b, times x plus 8, times the cosine of the angle, which is 60. Now, some of you may like to expand these brackets by writing 2 of them out. I would encourage you to try and do it in your head, if you can do, and then check it afterwards by doing the double brackets. Because that's the only way you'll ever get good at doing it in your head, is by doing it in your head and then checking it afterwards to see if you've done it right. And if you're right, all good. If you're not right, then adjust it and try and change what you were doing in your head. But we should be able to expand this in our head. What does the left-hand side expand to? Nabil, do you think you can do that in your head? 4x squared. Good. Good. And then here we've got an x squared. X plus 8 squared. Hassan, do you think you can expand that in your head? Yep. Yep. Good. And then here, what is the cosine of 60? A half. So I'm just going to just leave this bit sort of not quite expanded yet. I've got minus 2x, x plus 8. And when you do the cosine of 60, that is actually a half here. So this half that I have here cancels with the 2, because 2 times a half is obviously just 1. So I'm now going to do a bit of collecting of some like terms. I'll take it a bit easy. I've got 4x squared minus 4x plus 1 equals, and then this side, it looks like I've got 2x squared plus 16x plus 64. Remind yourself you've still got the minus there, so you've got minus x squared plus 8x or minus 8x? minus 8x. So you've got minus 8x. Okay, I'm still going to take my time with this because this is where we can make easy mistakes. So I've got 2x squared minus x squared, that's just x squared. I've got 16x minus 8x, that's just 8x. And then I've got 64. When I get to this stage, what do I need to do? Collect like terms, make everything equal 0. I think it's going to be easier to make this the correct side. So I'll take away x squared, I'll take away 8x, and I'll take away 64. So I get 3x squared minus 12x minus 63. And then I'm going to be lazy, and I'm going to use my equation solver. Okay, great. So I'm still going to just show everyone how we do that anyway, in case you're not sure. Polynomial 2 was 3, what was it, 3 minus 12 and... So you've got x equals 7, x equals minus 3. No, we can't put both values, can we? Yeah, because this one here is telling me I can't have a negative 3 here, but x has clearly got to be greater than 0, so x is equal to 7. Okay? So that's the kind of amount of algebra you might have there, where they've taken the cosine rule and they've used that as a vehicle to look at your other algebraic manipulation techniques and your idea of solving quadratics. And so this next question has not got any algebra in it, but it's definitely got a bit of like problem solving and about how you can look at something and try and see, try and see if you can build up what the diagram should be looking like. So it says Coast Guard Station B is 8 kilometers on a bearing of 60 degrees from Coast Guard Station A. Let's just pause at that stage that we've got to here, and let's just draw that first bit of information that we've already got. So which one should I draw first, A or B? You should say from, it's saying from A, so I'm going to start off with Coast Guard Station A, and remember that bearings are measured clockwise from north, so it's going to be 60 degrees. Well, 60 degrees is roughly like this, and this is going to be where Coast Guard Station B is, and that is 8 kilometers. This angle that we had here was 60 degrees. A ship C is 4.8 kilometers of a bearing of 18 degrees away from A. Calculate how far C is from B. So I'm just going to use a different color here to see if I can make this a bit clearer. In fact, I'm probably going to make my diagram just a tiny bit bigger, so it might be easier to kind of put some of these things in. So where is C roughly going to be? Kind of, yeah, to the left of B. It's going to be in between them because it says it's got a bearing of 18 degrees away from A. So let's go to this pen that we've got here. And it's only 4.8, so it's going to come up here like this. That's where C is going to be. This is 18 degrees, and that length of the line is 4.8. So you can see how a diagram can become pretty messy pretty quickly. And the thing the question wants us to find out is how far C is away from B. So this is the distance that we're trying to create. What do you think might be a good idea once you've redrawn, I've already said it. Redraw it, because it's kind of messy to see. So I'm going to draw out what this triangle looks like. This is the thing I'm interested in. And I know this is 8 and that this is 4.8. What else do you think I should be finding out then? Yeah, this angle here. Yeah, it's going to be 60 minus 18, which is 42 degrees. And then once you've got a diagram that looks like that, you tell yourself it's going to be the cosine rule because I've got all three sides here. So I can go pretty quickly and say that the distance squared is 4.8 squared plus 8 squared minus 2 times 4.8 times 8 times the cos of 42. And I'm going to put all that in my calculator, and hopefully we will get the same answer. So it's 4.8 squared plus 8 squared minus 2 times 4.8 times 8 times cos of 42. I'm also going to square root my answer as well, and I'm going to go straight to 5.47 kilometers to 3 significant figures. So just required a little bit of extra drawing that we needed there. Okay? Once you've done that one, I'd like you to have a go at the ones that are at the bottom of the page that say your turn. So I shall put these up here. And if you are doing this at home and you want to check, these are the answers.